You are almost welcome for this program. This is a 5 days online courses, and there are almost 2,000 registered participants from 340 institutes for this program. It is very uh, heartwarming to see that so much of registered delegates are there. Particularly, they want to learn about the numerical ocean modeling, which is also very important for present day context, because study on the ocean from remote sensing is a bit different than over the land, because ocean is very dynamic, it changes very fast comparatively to the land. So you need to take help of a lot of numerical ocean models for deriving various parameters, because all parameters cannot come from remote sensing of the ocean. So the models are very, very important to get the various kinds of parameters, and then finally go for the regional ocean model, other models, so that you can reach to a conclusion what you want to do study. So I feel that this course is very important, and all the participants, I think they will be learning few new things, and so that it will encourage their the thirst for the research over the ocean. So and for this program, as you have seen the timetable maybe by now, we have organized program lecture by Dr. Rabindra Nayak from National Remote Sensing Center. There will be scientists from National Institute of Oceanography. There will be scientists from IIT Mumbai. There will be scientists from Indian Institute of Remote Sensing. So I feel it will be very, very enriching course. And I also thank Dr. Nayak, because he is also busy, but he took out his time to share his knowledge with you people. And he does very good work on the ocean processes, ocean modeling. Now I give this floor to Dr. Sajiko Mohanty to tell about the courses, and please give a brief work report of the Dr. Nayak, what he has done so far, and give the forum to Dr. Nayak. Okay, Sachiko, please carry on.
Yes, sir. Thank you, sir. Good morning, all. Welcome again to the 166th Outreach Program on Remote Sensing and Numerical Ocean Modeling for Oceanic Processes. So today we have Dr. Rabindra Nayak to deliver the first invited lecture of the course on Fundamentals of Ocean Models. So before starting the lecture, I would like to give a brief introduction about Sir. Dr. Rabindra Nayak is a senior scientist at the National Remote Sensing Center, NRSC, ISRO, Hyderabad. He has expertise in the area of Earth observation, remote sensing, carbon cycle modeling, and ocean and atmosphere general circulation. He is currently holding the position of Scientist SG and head of the Land Surface Processes and Climate Studies Division of NRSC. Dr. Naik received a Master of Science in Physics from Utkal University and a PhD in Physics from Goa University as part of the UGC and CSIR NET Fellowship. Previously, he served as a scientist and faculty at the Indian Institute of Remote Sensing, Dehradun. He was a visiting scientist to NASA GSFC and JPL USA, International Space University, and Asian Institute of Technology. He has been affiliated with Central University Hyderabad, Andhra University Visakhapatnam, Jawaharlal Technological University Hyderabad for the guidance of PhD students. He is the reviewer for a number of national and international journals and has published more than 70 research papers in peer-reviewed journals. He is a recipient of the Professor P.R. Pisarito National Memorial Remote Sensing Award and a life member of the India Society of Remote Sensing and India Meteorological Society. He served as a member of national and international technical committees and symposium, including the IOC Group of Ocean Experts and the International Society for Photogrammetry and Remote Sensing. So with this brief introduction, I request you, sir, to please start the lecture.
Thank you. Thank you very much, Sachiko and Mitra, Dr. D. Mitra sir. And this is a good opportunity and privilege for me to interact with the students and participants from different expertise, maybe the early career people from the different organizations. And what I'm trying to do that, since it is a very fundamental of ocean model, so that I feel that if anyone having some kind of like if I go to the slide, if you do have some kind of interaction, please put your questions and raise those, and I'll try to answer them and try to clarify your things. So this is about the fundamental of ocean model. And there are like overview of my presentation. It is I'm talking about little bit about the why we need to the ocean modeling, brief introduction, and then what are the governing processes and differential equation, whatever the various process converted into mathematical form, and then subsequently solve in the computer programmings, and then with realistic problems. Then we'll talk about various applications starting from the global to the regional scales. And as you know that this particular slide talks about left hand side, you can see that kind of phenomenon occurring in the ocean. It has been depicted in the earth in a sphere, and some part of the Pacific Ocean, Eastern Pacific Ocean, you could able to see that Australia, northern side you have Eurasia, those kind of things. And the kind of phenomenon occurring the right hand side, if you see that kind of linear kind of structure, very condensed structure near to the coast, and then there are certain kind of eddies and guides that eddies of scale of few kilometers to several kilometers can be seen. And I'm not going to there is a video. In fact, there is a very interesting about how all the data are being put together to prepare the high resolution ocean surface phenomenon or circulation pattern. You can see later because time may be limited. So this is another slide I'm going to show that this is particular slide. It talks about satellite data. When it depicted from the space, you can see that left hand side, the ocean color data, it has a lot of variability, and with the different colors you can see, and flow pattern you could able to see. This flow pattern and color, you can see some kind of again eddies and very strong phytoplankton bloom. Those kind of phenomenon you can able to see that how the kind of phenomenon occurring in the ocean for like so much like compressed way and very small area. So many things is happening. Small area in the sense when you talk about 100 kilometer, 200 kilometer, 300 kilometer, and basin scale we talk about bigger gyres, which is of the order of thousands of kilometer or more than 500 kilometer radius. And the right hand side, you can see that ocean surface with high and low water level. From the photography it has been taken, and you can see that when you see that some part of the ocean, you can see that how the ocean different kind of surface topography is varying from the the background level. It is a varying, depicting basically the oceanic waves, and it's and white cap the white areas. And when this is in fact it is about maybe 1,000 by 1,000 kilometers total dimension. But when you come to the if you expand this, you can see that the white regions are the dissipation of energy of white caps. The energy when wave interact, they dissipate the energy, and in the open ocean as well. So this kind of phenomenon, if you understand that how the ocean, the variability varies from the small time scale or spatial scale of few kilometers to the several kilometers beneath in the basin scale circulation, and depicting of different kind of variabilities of wave, current, and bigger gyre kind of things. And this is one of the image. You can see that it is retrieved prepared from the our scatterometer. ISRO has a scatterometer, and for last several years, 93 to 2020, our ISRO data combined with the earlier scatterometer data, QuickScat, and other NASA data, it is a combined product has been prepared, and from that, ocean current has been determined using the altimeter sea surface side. And then if you just look at that, the kind of current pattern in the Indian Ocean, it prevails. And in that, you can appreciate that the coastal area and open ocean and coast and the equatorial belt, how the different kind of dynamic regions you can see. And then you coming to the down, the global ocean pattern, and you can see that the equatorial area, highly energetic area. Even if you go to the subtropics in the southern to the polar region, there is also convergence area. So it is a depict of the current pattern large scale, which is essentially the function of atmospheric forcing as well as many other forcing. So such kind of phenomenon happening from the few kilometers to the several hundred of kilometer scales. This is when we appreciate going to the modeling, we understand that ocean is very, very important in terms of as a part of Earth climate system, and it has a thermal inertia, means it absorbs the heat and it can remember the heat and store the heat for hundreds of years. And when ocean is not, we know that ocean is a fluid and Earth is rotating, and as well as that it is subjected to the various forcing. Therefore, the ocean current at the surface and the subsurface, as well as a three-dimensional circulation, baroclinic circulation prevail in the ocean, and depicting different kind of interaction with the atmosphere and making the global climate and weather systems, and by exchanging of the mass, energy, and heat with the atmosphere. And so that when atmosphere has a remembering capacity of very few days, but ocean can have, like, you understand that cyclone, many kind of tornadoes, all the things happening over the ocean. So ocean is a background which creates those kind of instability, and that once it is created, it is a propagating through the atmospheric waves and or flow pattern, and it is propagated one area to the other area. So all are highly coupled, and ocean has played very important role shaping our climate weather systems. So to understand that, like, that this is particularly depicting that in the simple how the ocean exchanges with the atmosphere in terms of heat. We know that heat budget term, we talk about latent heat flux, basically the heat at with, like, evaporation taking place, which carry the heat from the ocean to the atmosphere. Similarly, you have a solar radiation which is coming in, and when it is coming through the atmosphere, then subsequently it is interact with the ocean. Some part of the energy it absorb, particularly the, we say, the visible part, and those absorb, and this then subsequently ocean get warm up, and by the warming it is also radiate heat in terms of long wave radiation as well as a sensible heat flux. Sensible heat flux, we talk about, it is a equivalent to, we can say, conduction mechanism by which that basically that media will take place, that kind of vibration, like, conduction mechanism. And similarly, long wave radiation, basically the any, as you know, that any object at any given temperature, it can radiate heat. So ocean is a major heat radiating through the long wave radiation. Latent heat through the evaporation, latent heat flux is a bigger cooling process of the ocean. When ocean get cool and it drop the surface, basically daytime it is a warm up and night time it is cool down. And when it cool down, then surface water get cooled down, then it is drive the convective system to the down, it is dipping down, and subsurface water come up. We basically call convective turbulent mixing. Wind also can cause the turbulent mixing by transferring the energy, particularly you have like when force, like wind is moving over the ocean, over the rough surface, there's a through the friction, that the dissipation of wind stress or energy goes to the ocean, and when it goes to the ocean, it drives the ocean current as well as oceanic wave, different phenomenon it drives. The energy goes from the ocean to atmosphere to the ocean, vice versa. The ocean play a role the dragging the atmosphere energy. And similarly, that in terms of latent heat, like heat flux as well as movement flux, we have various biochemical fluxes. As you know that ocean and atmosphere share most of the common elements, and anything change in the ocean or the otherwise atmosphere, it drives the exchange process. And particularly carbon or nitrogen or oxygen, whatever we are in the atmosphere, they basically gas dissolution mechanism, it exchanges, and it is drive the kind of pumping, we say that, it drives the global carbon cycle and oxygen cycle, nitrogen cycle, all are been happening. And indirectly it controls the climate system through the biogeochemical cycle as well as the climate, like weather and climate, all the things are happening. Ocean play very important role. And as one of the small example, if I say that ocean, that what we breathe in the oxygen in the in the terrestrial animals, they require of oxygen, it is coming from the whatever happening over the ocean exchange. Almost 50% is recycled over the ocean biota, and terrestrial biota can make another 50%. So you can appreciate the importance of the ocean in terms of our life. So understanding ocean circulation and biochemical cycle is very, very important. And therefore, the processes occurring in the ocean of the small scale molecular time scale or spatial scale, which can happen few centimeter or micrometer level, to you have climatic scale of hundreds or more than time scales. So in between there is so many mesoscale or different time kind of time scale happening. Sometimes we say that seasonal time scale, seasonal circulation. Then when you mean over the whole season and annual, we say that annual circulation. Then when you mean over decade, we say decadal circulation. So that therefore the circulation pattern and phenomenon what is occurring in the ocean of the ranging from the few millimeter to the thousands or 10,000s of kilometer. So things are happening in one part of the ocean. It is processed through the advected or transported from through the ocean current to the like advection and to the sometimes it is a dipping down and coming back and to the surface water, subsurface water. So ocean three-dimensional circulation pattern which behave how it is happening and play important role for the modulating the ocean circulation and subsequently processes and interaction with the atmosphere and other things. So we appreciated that ocean modeling and ocean circulation, ocean play very important role. So understanding ocean is very, very important in terms of not only in terms of navigation, not in terms of the financial, but also life. Already given example is carbon and oxygen like sense and breathing of the oxygen by the ocean, which can like create oxygen for the land terrestrial animals. So similarly carbon, so food, all the things are happening and that is ocean play important role. So with that, so with understanding and the parameter measurement of the ocean is very important. And conventionally before satellite, lot many observation has been happened, and that is we talk about in situ observation, seaboard observation with the opportunity of sometimes you cannot have like plan like let us have 100 ships and go and measure everywhere. It is there is a lot of problems are there in terms of financial and planning, all the things. Therefore, historically, people have been measuring ship like if sometimes they take one or two ships and therefore they put also buoys to measure the ocean profile of the temperature, salinity, various properties. And and this data, if conventionally before 1970, if you think about that, for conventional measurement before coming to oceanic, realistic measurement happen, it is only whatever the observation is there, maybe 30 to 40% of the ocean is covered by measurement. When satellite has come, again satellite can measure the surface phenomenon, but it has a limitation. It cannot measure the deeper. For example, ocean temperature can be measured by the satellite through the thermal infrared channel, but looking at ocean surface. But if you go the 10-meter deeper or 100-meter deeper and 500-meter deeper, or even like oceanic depth, abyssal depth, if you go, the temperature is ocean cannot, the satellite cannot measure. Similarly, salinity can be measured by the satellite at the surface only. It cannot measure ocean, whatever the phytoplankton in the surface layer, it is measured. But therefore, ocean only surface part, most of the surface part can be measured by the electromagnetic radiation through the remote sensing technique. So, and therefore data coming from the observation in situ and the satellite are not enough to understand detail about ocean. So, and as you said, this is pictorial representation of that, because one space agency is not capable enough to put all variety of measurement of the space, like ocean or land, from the space. So therefore, there is a consortium like make up like different space agency coming together. They have shared their resources, share their knowledge, and put the different satellite to measure the ocean and land, all the things, and how much measurement will get better we can understand. So therefore, this kind of togetherness can help us to go do the better measurement of the ocean as well as earth systems. And this data still added to the in situ is not enough to understand ocean processes of a few kilometers to the few, few meters to the few several hundreds of kilometers. So therefore, what is happening? But observations is a instrumental to understand ocean, and even if development of model. Therefore, in the scientist has developed model, and when first measurement has done, somebody has gone, okay, temperature, how is the temperature of the particular water depth? It varies. Then come with that. Look, if this is a measurement, what is the how can I develop a model, physical model, looking at the various heat processes, heat flow processes, heat transfer processes in the water medium. There is solar radiation. So solar radiation and Okay, so and then all the heat budget term by means of which you can measure, then you can think about some kind of how the water get the heat get absorbed and irradiate, and putting them together you can develop a model. Similarly, water when flow, when people got flow meter measurement of UV, they started working on the how the flow happen in a channel. They develop some kind of a model. So those model in early days, whatever they develop, and when we talk about Earth is a rotating, therefore it is rotational system we need to flow pattern we will be calculating. Therefore, when early model has come with a lot of approximation has come, and this approximation still exists, and that is we are trying to improve those approximation and predictability. So therefore, when putting them together, when you talk about circulation model, its general circulation model means all kind of till today what we understood the physics of the ocean, putting them together, making mathematical governing equations, and then trying to the method we know, the analytical numerical method we know to solve, and therefore with help of advanced computing method, and so advanced computer. So when we talk about advanced computer, maybe if you go back 20 years back, people talk about it is a kind of high performance computer. That is now a simple computer now today. So we'll appreciate after some time that how much computer space we required to solve any finite element method. So if thinking about even a small area with high resolution phenomena. So till today also there are many things with this advanced computer we cannot able to solve. So general circulation model is abstract of all kind of mathematical formulation. Put them together, we talk about Navier-Stokes equation. And it is one of the bigger challenges today to solve a Navier-Stokes equation by the analytic method. And that is not done today. There is no such solution, exact solution possible. And why is not possible, later we'll again understand. And therefore, Navier-Stokes equation, it is a combination of mass balance equation, conservation of mass. If mass of a given ocean basin is or ocean packet is changing, that mass is changing, is maybe precipitation is happening and evaporation, water loss is happening, river runoff is coming, and there is a also somewhere salt like high dense water is flowing from one area to the other area. So it is talking about thermohaline circulation. So this is mass conservation equation. Similarly, movement equation, movement balance equation means if a object is undergo some acceleration or movement, it is subjected with some external force. So with the subject external force, what are the different external forces subjected to the water parcel and the atmospheric parcel? That will be putting them together. We talk about the equation of the movement balance or UVW, horizontal and the meridional, and that is your those UVW, vertical current, and zonal and vertical current that can be simulated or estimated. And how approximate, how corrective we estimate, that is matter. But importantly, we say that we can simulate or we can estimate. So similarly, sometimes energy balance equation, and how much energy is like it's a given system, how much energy it has a different form. As you know that energy can neither be created nor be destroyed, so it can be converted one form to other. Therefore, whatever the heat energy is coming, what is the kinetic energy is coming to the forcing, or what is rotational various form of energy is there, whether they are balanced, and therefore putting them together, we write that equation of thermodynamics, equation of movement balance, equation salinity equation, or the temperature equation we can derive and put them together with the proper initial and boundary conditions. It is both applicable for the atmosphere as well as ocean atmosphere general circulation model. So then, and you can look at that, what is Navier-Stokes equation? Please, it is exercise to you. Please, can you, if you get time, and can you go and check what is the equation? Okay, and generally, when you talk about ocean model, it is a general circulation model, has been like whatever their Navier-Stokes equation subsequently converted to certain kind of equation. Why? Because we don't know exact solution of those equations. That is, till today, Navier-Stokes equation cannot be solved. And when it is not solved, there are certain approximation we made, and this approximation based on scale, and those people have already studied. I can give you one hint that please you do the scale. Look at the Navier-Stokes equation. Look at your measurement, certain measurement in the bigger time scale or space scale, oceanic measurement, and then see that which which particular term is dominating, which term is not dominating. It allows you, scale analysis allow you to understand that, simplify the various terms in the equations. Sometimes non-linear term, second order term, you will appreciate that, advective term and diffusive term. Sometimes for when you see early days, people neglect that term and solve the only that linear term. And if I'm talking about, let us say 25, 30 years back, when the early ocean model came, and geostrophic balance only they talk about certain things, then corrected with western boundary current, those kind of things they took about, they solve. But now it is a situation, might be much of improvement happen because of computational power. So there are these Navier-Stokes equation are simplified to make a compatible for the solving, it is solvable equation they made. And this, based on that, there are certain ocean general circulation model today in practice has been used. One is known as Princeton ocean model, which is very, very early 1980s. It is one of the very versatile good model has been developed, and from that ROMS has been come regional ocean modeling system, then subsequently modular ocean model system or hybrid coordinate model system. We'll understand why this different coordinate, different approximation is required for the solve and which are the process. Therefore, there is no universal model such to address all the problems. So therefore, today, if you want to forecast a system, which process you need to forecast, then you have to choose such kind of model. And so by assuming other things are like not much important, or in the scale analysis, it allows you to do that. So therefore, you cannot, today we don't have universal model such for the ocean or atmosphere. We have a very, very special models are there. And these models, basically we talk about, you have a space, three-dimensional space, as well as the time. Therefore, four-dimensional space. And we need to, that advanced computing system, we need to discretize those equations, because as I said, that analytic solution has very, very limited application. If you know that analytics exact solution, if I give you a differential equation, all are coming as a differential equation. And this is different second order, higher order, second order coupled equations. And solving those coupled equations of second order is not possible by analytic method. And there are various methods in physics. People use series solution or different polynomial approximation, or there are different ways. One of the method is a versatile method, is a finite element method and finite volume method, or finite difference method. So I'm talking basically finite difference method, and this used to solve most of the ocean large scale model. Today the GCMs are based on the finite difference method. And they are useful for predicting ocean state at varied spatial temporal scale for operational purpose, ocean state nowcast and forecast purpose, and again to understand climate. So already I talked about that ocean examples of various ocean general circulation model, and these models has the global and regional application. With same model, you can, if you want to study a limited area model, let us S3 or Bay of Bengal or Arabian Sea, or maybe some part of the any part of the base of in the global oceans, and you want to study that, then you can use that, but with limited certain things you have to take care, proper open boundary conditions, those kind of things. So when you talk about ocean general circulation model application for different problems, we should understand that is whether we are going for global application, large scale application, or the very small S3 applications. Then we should worry about, because these are the finite difference method and discrete Taylor series. You must have, please you go through that, how people are discretizing those and taking various stability condition. If you take when each approximation, basically finite difference method is approximate method, and in a given grid system, if you know one grid, let us say x1 y, first x1 y1 position, you need to calculate x2 y2 position and x3 y3 position at a different time. So then therefore creating particular grid is very, very important. You are solving in an Earth system, in a sphere, maybe limited area, maybe Cartesian grid, you need to do that. Therefore you have to define those grid, and all the equations are converted to the each pixel, how those equations look like. Then there is a, when once you converted differential equation is a system of linear algebraic equations. It is a, when you convert nonlinear equation, differential equation, there is a Taylor series allows you to discretize it and make it a like algebraic equations. Algebraic equations means, I say that, let us say 2x plus 3y plus 5z equal to 0, like 3 variables x, y, z, and you have 3 different such equations you get, then we get the exact solution. Same thing is happening. All the like all the like governing equations are converted into the discrete equations, and with certain, and while converting discrete, you should worry about what delta x delta t I need to take to make my grid or come to, so that I'll get a stable solution. And the solution will not be like diverging from your approximation, or diverging to your what you believe. So therefore, there is a certain mathematics and physics allows to define your delta x. We say that computational fluid dynamics CFL key like criterions, and that constraint what is the largest fastest gravity wave propagate in your grid. And by the way, you have lot of turbulent, you have convective schemes are there, and you calculated how they couple them, and those solutions should not be diverse. There is a that is a delta t, delta x, and the c velocity of the particular wave which you want to model within your approximation. They should be delta c, must be your delta should be constant to the delta x by delta t, must be greater than less than equal to c. You need to do that condition. So, and there are higher order conditions also there, and it is a simplified condition I'm talking about that. So when modeling, you must worry of those, whether any grid cannot be, when you supply your model, any grid you cannot think about. Again, sometimes your bathymetry can create the instability because of many reasons, and therefore we need to smooth bathymetry. And there are many parameters you need to smooth to model. Therefore, every cases you are smoothing and getting the simpler and approximate solution. You are might be, because of uncertainty may grow. So avoid to that. You need to do that, and check and balance you need to do with certain interval of time where my solution is under my control or not. That you need to do that. Okay. So sometimes what is happening, and this, and also this model initial, t equal 0, we should know all space, all grid, what is my initial condition. In 3-dimensional state, every places I know all parameter I should know. Absolutely, it is not possible today to know. For example, ocean current, I may know surface, but I don't know abyssal depth. I know one place, but I know the other, I don't know other place. Therefore, problem is that approximating some initial condition, as you know that it is a non-linear differential equation, you are going from the unpredictable situation. So therefore, boundary forcing, the initial condition, a certain way we can make it be like but delta change in the initial condition, our prediction can go away from the. Therefore, we need to check and balance. We need to do that. So then another thing is boundary forcing. Yeah, as you know, boundary forcing, we need ocean is an open boundary at the surface, and there's a lateral boundary. Sometimes, if you limited area model we do, and sometimes glacier and snow, and glacier and water, they are combined, and sometimes continent and water. How the in the upper closed boundary, then open boundary, what is the things are happening? At the bottom always closed boundary, in the surface it is always open boundary, and lateral there is a estuary and river, there is a what kind of boundary condition you need to put and similarly all boundary condition you need to understand what is the realistic boundary condition, and from where I have to data to supply those boundary conditions. Then having all these things, sometimes happening that forecaster that some model are used for this with different purpose. One of the purpose is that predictability, understanding those kind of things. Other things is that forecast and nowcast. For nowcast prediction of the ocean state forecast or the atmosphere forecast, these are the very much operational basis you need to give with certain uncertainty level. Therefore, what is happening? You don't know, a model is not 100% control on you, like under you. And therefore, we need to data simulation concept. We need to check, as I said, that when you have a forward model, after certain time, it may deviate from its state. So you have to bring back to the state, to the original state or the believable state or approximate realistic state. And therefore, you to take the other data to constrain. We say that constraining the data to the ocean model with a data assimilation. It may be data assimilation can be a simple problem to a very, very complex problem, and depending upon our ability to assimilate the data and observation available. So these are the important ingredient of a ocean circulation model. Then, as you know, that this all the data, these are just the globe. You need to have an initial condition, you need to have a boundary conditions, and you need to have data to constrain. Where you get all the data, you need to plan for that, or you continuously measure. Fortunately, satellite give ocean surface which is open boundary conditions, and now we are able to get most of these surface fluxes, including heat flux and momentum flux and temperature, like all the fluxes, approximate level we know, and satellite can give good observations. So these can be used for the forcing parameter. But initial condition still problem. And we sometimes will talk about how the initial condition model can be spin up and to have because physics also allow something to come to when you start with a delta solution, it will get a mix up and then come to a certain believable state. We say that it is a spin up or the ground state we can bring back. So ground state generation, we can do that, and by spinning up the model. So when I talk about all the things, put them together, I have been using I have experience, and particularly Princeton Ocean Model, as well as I have a regional ocean model. We are now working on that, and I have put them together. You look at that schematic way, what I told you. So I put them together. We have a governing equations, and it conservation of mass, conservation of momentum, conservation of energy, equation of state, mixed layer, turbulent closure scheme, all are putting them together. And with the boundary forcing IIRS interface, I need to put heat, radiation, momentum, evaporation, precipitation, lateral forces, lateral also boundary condition, all them I'll put them together. And then we force with the initial boundary, lateral boundary condition, we can run and get the simulated value, physical state of sea level, ocean state, particularly composed of the water level, temperature, salinity, and horizontal and meridional currents. And we should have a three-dimensional also vertical current we can get. And sometimes we club the biogeochemical cycle. And it is sometimes people use it as a offline couple, sometimes like a feedback mechanism way, online couple. So we use it offline. Our physical model is not impacted by the biogeochemical process. Our physical model simulate the temperature state that will go as an input to the biological model to drive the biogeochemical cycle. So this is a very simple way representing the schematic of the model and of different processes it has taken into account. And already I talked about that governing equations of the ocean. It is like, it is, as you know, Earth is rotate. Earth is a rotational frame. When water is rotate along with the Earth, anything sitting on Earth, it will be rotate along with the Earth. When it goes, then there is a Coriolis force. I know any fluid, if start moving, it is deflected towards the right. So it will get Coriolis force. The Earth rotation play important role. Another thing is that when water move, when it is reached to the land lateral boundary, some land is there. That side it is a pile up, and it will increase the height. So then it creates the gradient of the pressure, and then for pressure gradient, then it creates once pressure gradient created. Then it is under the rotation, it has to move. We talk about balancing pressure gradient and Earth rotation. We talk about geostrophic current. You must have known. Only simplified, only two equations we use, and then we get that. And then wind, Ekman forcing, which is wind drive wind blow over the ocean, and it creates the roughness of the ocean, and energy is dissipated in terms of stress, as well as in terms of some small scale energy like wave it create, and that ocean. Then tide is another kind of forcing, celestial bodies, tide like sun, moon, they have tightly coupled with respect to Earth. Hello. 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 Yeah, please. Hello. Yeah. मीटिंग हो रहा है. I am busy in a talk actually. Giving to IRS there, please. Please. Sorry for taking little time for other things, please. And let we continue with that governing equations. As you know that tide is, we stop at the tide. No, tide because of sun and moon, and they have tightly coupled with the earth. Anything's happening, and ocean basically the fluid. Even if land also, there is a land tide. Terrestrial tide is also created. Atmospheric tide also created. In ocean tide, or it is a pulled one side when towards, let us say, sun and earth, no, moon and earth, and so moon try to pull towards it, and then opposite side also, when the earth is earth total mass also little bit pulled, therefore opposite side also there is another bulge occur, and then both the sides, so water level will be high. And if you think about three body problem like earth, moon and sun, then how the tidal forces means, it's simple. We say that gravitational force modulation, or like kind of differential change of the gravitation force among the various celestial bodies, particularly moon and sun on earth, drive the tidal forces. And that is it. And then as you know that these forces are external. Now buoyancy, because of heat and heating and cooling occur are the earth, like ocean surface, and ocean get when it is a cool down, then it has to density will be increased, and it has to that deep down, and then water which is at below, it will come up, and which is a convective, we say convection or buoyancy driving forcing, and it can drive. It is known now whole world ocean circulation, like climatic time scale, buoyancy or the we say thermohaline circulation is a major current system which is created by this mechanism. And as you know that ocean surface tension, if surface, every fluid wanted to maintain the minimum surface area, if any deforming forces try to increase the surface area, it try to come back, and therefore those kind of things create also important role for the small scale processes. And Earth gravitation, as you know that Earth gravitation always there. If anything is going out, it has to pull down. So it is a force is there. And barotropic or baroclinic circulation, when you talk about that, these are the concept particularly. Barotropic, when you talk about that, it is a layered flow, like a given layer, and there is a no interlayer flux of flow occur. And when interlayer flux is occur, we say the baroclinic, where pressure and temperature density gradient exist, and there is the gradient have a, like there is a kind of angle between them, or they are not parallel, and density and pressure field, they are not parallel, and therefore there's a possibilities, there's a flow from one layer to the it introduced to other. So this a kind of a baroclinicity occur when there is a baroclinic instability, or there is some kind of forcing occur. But otherwise, in the 70 to 80% of oceanic water is a barotropic. And right hand side, we say that there are many kind of processes. When you talk about one scale, it is a very small scale, certain scale it is high, like it is wave. In other scale, it is a small scale system. So therefore, in the nature, there are different kind of waves, patterns, tides, Kelvin wave, Raji wave, Poincare wave. Different name has come because of different scientists, and they develop, they find out different peculiar kind of wave phenomenon occurring in the ocean, also in the atmosphere. They named as such. So any of the equation logician should able to solve, to predict those known phenomena. These kind of wave should be able to simulate. Otherwise, we say that those models are not planetary models of planetary scale. We cannot apply them. So therefore, basic check of those model, certain fundamental things you need to check. Now same thing I talk about primitive equation model. I told that certain hypotheses are there. And I don't talk about that bushiness and what are incompressible, various things are happening, and then model get approximated. And this is basically the schematic of the differential equation. Like these are the boundary conditions. Okay, various boundary condition we need to are the surface, as well as when you have a look at all the equations, and like if we say that primitive equations, there is a moment balance equation, mass balance equation, and then there is a diffusive process. The fluxes are the ARC interface, and inside also diffusion. Then they are parameterized in terms of the like those very small scale processes are approximated to the large scale processes. We talk about that closure scheme, various closure scheme. So, and also various coordinate system people use. Sometimes people use sigma coordinate system. Sometimes people use the constant layer depth coordinate system, parallel layers, solve the equations. So in different coordinate system, how the boundary condition look like, those can be seen it. And KMV is the eddy diffusivity for the movement, vertical movement, like horizontal movement. Then and temperature, similarly temperature and salinity. And here tau x is the surface, since it is a surface, and so this is a tau x is the surface wind, particularly wind stress. And then you can go through that, and this is the surf that then bottom fluxes are the ocean bottom. This is left hand side, basically the surface, and right hand side bottom boundary condition. And then there, what is happening? No slip condition would be taken. And like ocean open boundary, there is a always continuous forcing, fluxes of momentum. So bottom also there is a continuous bottom drag and forcing. But the eddy diffusivity, which is zero, but at the surface, there is a eddy diffusivity in terms of evaporation and precipitation, heat fluxes. All the things are there. Water flux is happening, as well as the momentum flux is happening, and heat flux is happening. So that is a major difference between the open boundary at the surface and the bottom boundary condition. And these coefficients also subjective. When you do the run, maybe people have given this coefficient some particular properly parameterized in terms of length scale, otherwise some constant number they have given. And you need to check which, like with certain measurement, you need to check how to, which coefficient I need to use, or can I increase or decrease, can I sensitivity study can allow us to fix the coefficients. Certain things you need to take care. Now this is just showing that upper boundary and a mixed layer. As you know, ocean circulation, sometimes what is happening, we take the ocean circulation, lot of mixing happen at the surface, and also bottom it is happening. Therefore, those mixed layer, how different kind of mixing scheme has come. One is simpler way, it is been said here, but there are different way mixing scheme, 1 closure, 1.5 closure, different closure scheme has come. It has a different boundary layer theory. You can go through that. It will give you, allows you to understand much more and see that what process you are looking for, how you sometimes, large scale circulation, you may not be interested in the mixing at the surface that much faster or that, but simple. Therefore, we put only certain salinity we force there instead of heat fluxes. So there are different, like when you do the modeling, you have to plan what purpose you are doing. And so this is another, like, how to tune those coefficients people have done in certain area. You can see that gamma 1 is 3.10 to the power minus 4. So like 3 into 10 to the power minus 4 meter per second, 2.5 into 10 to the power minus 3 meter per second. Like that quadratic, these are the various coefficients. Some people take it very specific cases, drag coefficient for the bottom. Surface also, you need to tune that properly. And so, as you know that we are solving in a grid, therefore it has a closed like continent and the land, ocean and the continent, there is a boundary, and we have to take care of the closed boundary. Similarly, there is a limited area, suppose Bay of Bengal you are doing, then only Bay of Bengal limited area model. So south is open boundary, and what is the flux you need, normal flux you have to take care. So those kind of things you need to, sometimes people talk about periodic cycling because you don't have realistic flux at the boundary. Therefore, you have to take from other model and allow to do using periodic boundary condition or like cyclic boundary conditions, or you can use realistic flux boundary condition. Different conditions you can use. Otherwise, your model output will be deviate from your expected or realistic values. So as already said that there is a global, like each grid you need to solve. Therefore, you divide into whole Earth into grid system. If it is a spherical or it is a Cartesian, doesn't matter. You need to understand that and you need to create those grids. And then each grid you need to solve. And here it is given is a delta 3.6 degree grid. And now this is the pictorially representation of continent and ocean and the grid, how it look like, So, and there is a, when such kind of grid is there, therefore, which model, which kind of boundary condition you need to take, which kind of vertical coordinate you need to take it, whether sigma coordinate you need to take it, or whether h coordinate you need to take constant depth coordinate. So that those constant layer coordinate systems you need to take. So horizontal, like vertical direction. Horizontal direction, maybe people are taking Cartesian, people are taking curvilinear coordinate system. And curvilinear coordinate system take care of the flow along the curve line. It has a better approximated value, better results it may give for the coastal area. Similarly, sigma coordinate will give better area in the coastal area. But if you open ocean, if you go, and if you are not much interested about very much coastal, then you can use Z coordinate system, and obviously you can use your Cartesian coordinate system, and for the limited area model, and you can get the reasonable solution for the seasonal scale or the annual scale modeling. But if you go to the high resolution temporal scale, those may be deviating for that. Maybe you are interested every hour, 2 hour day, those models will be highly deviating from your results. So you have to think about much about that. And then this is a kind of a vertical grid people have been using for the depth. Okay, so and okay, I'm not talking about wind, like important is that when you have a model, you need to have a data to either initial, either forcing. And here we talk about forcing, means are the ARC interface, what are the forcing? With forcing talks about movement of flux, wind data you should have. And it is reanalysis product you can use, or maybe a satellite derived reanalysis product you can take, and wind that will allow you to do. Buoyancy forcing, basically the heat fluxes, latent heat flux, sensible, and all the things. And then it is basically indirectly estimated from the SST and other data, and it is been satellite also derived such data, reanalysis product it is available. And then you can take, then salinity fluxes are the ARC interface, you must worry about evaporation, precipitation are the ARC interface, and you also worry about river runoff. So river runoff, those data. Then tidal forcing, obviously today tide model amplitude and phase very nicely can be modeled. That is a part of this, very much understood. You no need to force that, but limited area model you need to force it. And data initial condition sometimes we get from the climatological data, and therefore this data may not give you proper understanding. For simulation, you have to spin up the model. Sometimes it takes several years to 50 years for the climate model. Therefore, other alternative is that if once one people have done very much good model, you can take that as a initializing to your model output model. Then we say that reinitializing, or we say that taking out from believed model, you can reinitialize that, and you can do that. So already I told you that data simulation can be used for improving the model, but it is not model like improving model predictability. It is additional tools. If you have to, you believe that your model is not able to capture or this, your operational need, those kind of things. And sometimes this data simulation help you to properly parameterize your model input also, model parameter. So this is a different context is that it is a very elaborative. We can discuss in some other lecture. Maybe you can read and get to that. And I'm not going through this. So you know that these particular things, various applications are there: ocean state forecast and disaster risk reduction, understanding ocean process, biochemical cycle to climate change, and impact assessment. Ocean model can be used. Okay, so this is a kind of we have a ocean modeling forecast system by INCOES. They give that model prediction of global. You see that in left hand side there is a bigger grid, and then there is a nested, 3 different nested to get very high information about coastal area. They can able to do high resolution for whole area, but computational intensive, and therefore to avoid that, so bigger coarse grid can be done over all area, then nested over the moderate grid, then but while doing so, we need to consider how the boundary condition propagate from the coarse grid to the sub or high resolution grid, that to be taken care properly. There is other kind of model. You see that ocean model, whole global ocean circulation can be given with the vector you can have, and color as in terms of that significant wave height. You can see that. And people have been using different kind of ocean model at INCOES. They give ocean state forecast for the even if local in a specific domain basis, Bay of Bengal, Arabian Sea, or total Indian Ocean, like that. So okay, so at NRSC, what we do at NRSC, we basically the satellite data we need to take certain process study to examine that like interesting area, science, basically research problem we take care. So to do that, various research problem we have done in the past. One of the such things is that understanding high resolution ocean current system and continental coastal current system around India. You can see that you cannot get in the global large scale circulation model. You cannot create such kind of map. Residual circulation, which I basically remove the circulation of the highly tidal forcing. Remaining I have taken, I can able to show you the different kind of high resolution, very much towards the coast, very strong current system is prevailed. That, and part of that I show that right hand side, that Gulf of Hooghly in the east coast of India, that you can understand that how that model output is able to explain the particularly areas, those kind of things are occurring in this area. So this model we use for the understanding tidal circulation, wind circulation, and here it is a tide, create the tide from the regional model forcing at the boundary. And we know that open ocean, what should be the tide I force, but the inside I don't know. I need to calculate the water level. Then I create the amplitude and phase map, and I compare with the model observation and how the model is working. It is to understand that how does like our Sarala altimeter data is able to capture the water level near to the coast. So this is another such examples. Right hand side, you can see that the various oceanographic phenomena here, thermal front, the red color is, you see that they are the thermal front. We calculated for long term. Then thermal front, basically the regions of the high thermal gradient exist, and different layer of water like laterally. So this is the area of high high nutrient rich area and allowing to highly productivity occur. To understand that what causes that, we have a high resolution bathymetry. We create the ocean circulation and superimpose that and trying to understand whether we are able to simulate salinity so that SST properly or not, thermal front properly or not. And chlorophyll also we superimpose. We see that we are working towards to understand the chlorophyll dynamics. And this is another such examples about tidal circulation in the west coast of India, Gulf of Khambar, and estuary model. It is a limited area model. Ocean general circulation model. It has a western boundary and east like southern boundary. We provide the input fluxes and created the tide and wind driven circulation, and then high tidal dissipation energy, baroclinic tidal potential energy, which is it's put it here, and divergence of the tidal energy region are highlighted. You can see this, and other part of the globe also you can do similar way. And this is the kind of tide around the India coast, how it propagates. and using simple model forcing with the tide, we can able to simulate that. So we also use to high resolution model to understand the oil spill transport, those kind of things. I'm not going, time is over. Thank you very much for your patience and giving me opportunity to talk about that, about ocean modeling and its fundamentals. Thank you very much.
Thank you, sir. Thank you for very interesting and informative talk on ocean modeling. Sir, if the participant have any queries or questions, so you can ask.
If there are certain questions, can you read? Otherwise, I can look at that.
Yes,
Box.
yes, sir. I'll read, sir. I'll read. In case of ocean current, are we not considering the gravitational force of Earth and Moon?
Yeah, Earth and Moon basically tide, no ocean current. Basically, today practice is that in the large scale ocean circulation, particularly people are understanding the seasonal circulation. Though tide is very, very important, Earth gravity always there, a gravitational force, but the tidal force is sometimes people take or sometimes people not take. In practice today, a general circulation model, most of the cases, they don't take into account because it has a certain, maybe uncertainty would be there. We need to take it.
So next question is like differences in temperature and salinity create density variations. How does they drive layer-wise ocean current from deep ocean to surface ocean?
Yeah, so that what is happening if, let us say, it's obviously salinity and density is driving the like salinity and temperature driving the density. It is known by means of salinity. Let's say like let us say some water flash fresh water coming from the somewhere. Let us say a Bay of Bengal in the let us say river runoff, it is coming. So it may that it's a surface, it will be there, but gradually it is affecting the depot, and it is there. But that kind of buoyancy driven fluxes is been seen during that cyclonic activity, convective activity. But otherwise, with large scale circulation, long time scale circulation, thermohaline circulation, basically that whatever the ice melt in the polar area, for example, if it is a melt, and then it is a surface water. But somewhere area, when it is flow, it is a depend somewhere in the Antarctic area. Then that subsurface water comes again to fill the gap. It is a large scale conveyor belt, and it is creating the geological time scale. So very short time scale convective system when cyclone things are happening, and that. But importantly, how it is happening if low density is there by, let us say, salinity somewhere, it is a complex. As you said that depot, how it happened to the surface. I said that surface, how it happened depot. So this is if depot, if density is somehow that if hot water came somewhere, it is a less dense. Then it has to come up to the surface because buoyant, it is a less weight, it has to come up. And to fill that, nearby water has to come there to fill. So this drives the convective. So it is a very, very complicated system, but we can use that, the simple concept, and then allow the model to do all the things, explain that. Yeah.
So the next question is, what is the optimal model resolution for studying oceanic processes like 25 kilometer into 25 kilometer?
That already in my point, sometimes I told that that is that condition that that is a computational fluid dynamics that allows you to define what is delta t and delta x, which is the fastest gravity wave you talked about, that has to be captured in your model. So if you are certain constant that this kind of simulation I need to do, so that is my delta x, delta y. I need to take. For example, if I want to capture the tidal information, even if at 20, like 25 kilometer, I need to worry about delta x much smaller. Therefore, but it is may not be, those waves may not be considered in general fluid dynamics condition. So you have to think about when you put that, whether there is a first order condition delta x by delta t, there is a higher order, there are different stability conditions are there, and for approximating. Therefore, you need to re-examine those conditions in simple say that maybe delta x 25 kilometer, delta t, maybe you have a 5-minute scale, you can able to do that, or 1 minute. But there are certain scale 25, you cannot say that it is I have to take a 20 to 15 minute or 30 minutes. Atmosphere you may have maybe 100 kilometer you can have, because that atmosphere is highly compressible. So therefore you have to think and check your balance and what is your condition tells. And also you see that there are other bathymetry, other can cause the instability, not only the delta x and delta t. CFL condition we talked about. Yeah.
So one more question is, sir, can we please repeat the coordinate system of 3D model of ocean again?
Coordinate, you see, Earth, you see, when you look at that total Earth, you need to ocean, total one ocean you need to model. India, Indian Ocean, Pacific Ocean, Atlantic Ocean, all the things together you want to model. Perhaps the spherical polar coordinate system you take. Even if one basin of a bigger scale dimension, you need to take about a spherical polar coordinate system for the horizontal grid. But when sometimes we go for the smaller area, let us say some estuary or some small area, a northern bay, or like that, we may not take a spherical polar. We can approximate to the Cartesian coordinate system, and then we can convert that. And that is one thing in terms of. Other end is that curvilinear spherical is a curvilinear coordinate system. And when coastal, there is a continent boundary, like land boundary, are so much modulation, so much projections and things are there, so that very much undulated. Therefore, it is better to use the curvilinear coordinate system. And for the horizontal and spherical polar coordinate system is a special part of that, very simplified version, and for the whole Earth. And when coming to the, but if you take spherical, it is a good. Even if small area also good, but there are other problems also will get, whether you have to project your all the input parameter to that scale, to that projection or not, and all the things you have to take care. And otherwise, then this is a horizontal grid. Coming to the vertical grid, sigma coordinate people are, there are 3 different coordinate people are using. That constant density gradient, grade density, we say that parallel density surface, we take it. And then other one is people earlier pop model, those kind of things, they have taken that kind of model. Other one is a Z coordinate. You think about, let us, I have a total depth is 3 kilometer. I have to take each, like the total depth, surface layer maybe 50 meter, then another 100 meter, then 200 meter. I can divide into even if different width, but it's a constant throughout the horizontal direction. All the horizontal space, I take the constant delta Z scale. And that is one. You can, that is Z coordinate model. You can also equally divide by whole depth into 100 layers. You can do 50 layers. You can do. That is Z coordinate model. Other coordinate model is people talking about sigma coordinate, because you know that when continental shelf and coastal area coming to abyssal depth, the depth varies from 20 meter or 10 meter to the 3 kilometer or 5-6 kilometer. The scale it is happening. So what is happening? That flow parallel to the constant, like always flow trying to have in a laminar way. It is a flow. So to capture and follow the geometry. So therefore, it is a obviously barotropic flow always follow the geometry. So therefore, geometry is, if it is a kind of bowl shape, you must create the bowl shape. So to constrain those kind of solve a better approximation. So what is your important, what is your interest? So that nowadays people come with that lot of uncertainty coming one model to other. Therefore, hybrid coordinate model or unified coordinate system, if it is required to open ocean Z coordinate, because you no need to tell computer do so much computation. Open ocean process are simpler, so that you say that you relax there. But coastal or transition area, you need to high resolution. So therefore, you combine all the things together, you can, provided you have that kind of knowledge and technology and as well as computing facilities. Yeah.
Yes, sir. These are the questions, sir,
Yeah.
from the
Thank you very much. Then thank you very much. Yeah. So
okay,
then,
thank you very much, Dr. Rabindra, for your nice lecture, and I think it will encourage the students to do more work in the ocean models. So thank you very much that you could have given this lecture in spite of your busy schedule. Thank you very much once again.
Thank you, sir, for giving me such opportunity. Thank you to all participants for listening and giving your feedback and your questions. Thank you very much.
Thank you.
Yeah, thank you.
Thank you, sir.